This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Support for this episode comes from SingleStore. Scaling modern SaaS is hard. It's even harder when you're using databases that were built the last time boy bands and low-rise jeans were all the rage. SingleStore is a modern cloud database built for today's data-intensive applications and the smart SaaS generation. SingleStore powers the new wave of SaaS technologies, displacing legacy providers. Use it to break the data bottleneck and reduce your monthly cloud bill in the process. Learn how SingleStore can help you at singlestore.com/SERadio.
This is Philip Winston for Software Engineering Radio. My guest today is Audrey Lawrence. Audrey is a software development manager at Amazon. Her focus there is on their new database service, which is called Amazon Timestream. Audrey has worked in the software industry for more than 10 years at companies such as Microsoft, Uber, Cruise Automation, and Carmera. As a disclosure, I first met Audrey when we were both working at Carmera a few years ago. Let's start at the top. What is a Timeseries database?
A Timeseries database is a database that is purpose-built for time series data. And when we're talking about time series data, what we're talking about really is data points that are measured over time. So this is useful when you're measuring events that change over time. So when you're not just interested in the current measurement for some metric, but you really want to look at the measurements over a period of time. And you see this commonly in a number of industries. And actually, this is also a really fast-growing data storage type that we see across industries. And what time series databases do are they allow for really efficient collection, storage, and analysis on top of this data. So everything from doing streaming analytics in real time to maybe training machine learning models off of historical time series data. And these databases really allow for some complex analyses as well that you do on top of time series data. And what Amazon Timestream is it is one of these purpose-built databases for time series data.
Okay, so I know the financial industry has long used or produced time series data. They have data going back over 100 years on stock prices. So to get specific, what other applications or industries tend to produce time series data?
Yeah, finance is definitely one very common example that you hear for time series data. So looking at stock prices over time or different prices of commodities. And another big area that we see a lot of time series data is in the systems monitoring use case. So a lot of developers now and engineers want observability into their applications and their infrastructure to have really granular metrics about the performance and to ensure that things are running well and systems are healthy. So you see a lot of times developers will add metrics to monitor different latencies of components, different response codes, that type of thing. And actually one of Timestream's biggest customers is a video streaming service. And they use Timestream for this use case to monitor their video streaming content. So collecting metrics like frame rate drops, latencies, that type of thing, so that they can ensure really high quality content streaming to their customers. And this use case also, you get a lot of data at times. We can see up to gigabytes per second of ingestion and really up to millions of queries per hour. Another big area where we see time series data is with the Internet of Things, the IoT space, both in industrial settings and then also commercial settings. There's a move to kind of instrument everything and create smart devices. And these collect a lot of telemetry of the world around them. So thinking like smart home sensors, your smart thermostat that's measuring temperature, air quality, those type of metrics over time. One that I've gotten really used to is a smartwatch that I initially got as an upgrade from my $10 stopwatch for running to measure pace while I'm out running. But since I've gotten it, I've become really accustomed to all of the metrics it's collecting at all times, things like heart rate variability, air pressure, that type of thing. And we'll see this area grow as we start to make everything smarter.
Yeah, that makes a lot of sense. And for monitoring a data center, I can imagine there's thousands of machines and many more metrics. And for consumer devices, there could be millions of devices. So I can see how the scale is going to add up. So I think anytime there's a new type of database, one question that comes to mind is, why can't developers store time series data in a SQL database or a key value store or some type of database that already or has existed for a long period of time? What limitations or problems might they experience if they did use a SQL database, say?
Yeah, so developers certainly can use more conventional databases to store time series data. I've done this before in the past as well. But the problems that you tend to run into are around really scaling those systems out for performance and costs. Given time series databases just are purpose-built for this type of data, they can do a more efficient job in ingesting, storing, and querying the data. Another area too that kind of gets teams to adopt time series databases is the tooling around these data stores. There are a lot of different plugins you can use to really easily collect and ingest these metrics, and then also visualization tools that help later with querying and that type of thing. And then another piece too that kind of moves teams to look into using time series databases are just the solutions that they may need to come up with in order to store time series databases can get rather complex and can take a lot of developer time to build and then to maintain and scale out these systems. There was a recent All Things Distributed blog post by Amazon CTO that discussed this a bit and referred to these systems or compared them to Rube Goldberg machines, where we've seen teams manage their time series databases with really complex architectures where they need some system that can essentially like queue the data coming in, store it in some sort of durable store, have some massive parallel processing framework that processes that data and stores it in an optimized format for querying. And these solutions are pretty difficult to build and maintain and really scale. And a lot of times the metrics that you're storing in these stores are also your really critical business or operational metrics, which need to be timely and correct. So moving to a solution that can solve a lot of these problems for you, and also if it can do it in a more performant and cost-effective manner, means that you'll see it may just be the right choice for your team.
Yeah, that makes sense. So you could start out with a SQL database for a smaller implementation, but you're going to run into trouble with scale and other factors. Let me take a minute to list some relevant past episodes of Software Engineering Radio. This is the first episode we've done on time series databases, but many past episodes have dealt with other types of databases. These are just a few. Episode 102, Relational Databases. Episode 165, NoSQL and MongoDB with Dwight Merriman. Episode 194, Michael Hunger on graph databases. Episode 417, Alex Petrov on database storage engines. And I will put links to these episodes and the blog post you mentioned in the show notes. So let's dive in. Let's start with data modeling. How does someone create a data model for a time series database? And how is this different from modeling for a SQL database?
When you're using a time series database, the core unit that you really care about are what we call records. And this is just a single measurement of a metric at a point in time. And a series of these measurements over time is what makes up the time series. And for each of these time series, you have a group of attributes or dimensions that kind of describe that time series. And then those you can store in databases and tables to organize the data and control access, retention, and that type of thing. So an example of this would be if we are monitoring a fleet of hosts in our system, we could have a DevOps database and maybe a host metrics table. And then the dimensions that we would want to store with our time series to describe the different time series would be things like region where that fleet is located, host name for the different hosts, OS version, different things like that. And then the measurements that the actual metrics we're collecting. So things like CPU utilization, memory utilization, and traffic, network traffic, IO, those type of measurements. So those are the main concepts that you would think about when ingesting into a time series database, and based on your use case, kind of model what business metrics you're collecting into that type of format, which most time series, as you're thinking about, can really fit well into that. And time series databases also tend to have really flexible schema. So for TimeStream, you don't, outside of creating a database and a table, you don't declare your measurements and dimensions up front, but you declare them when you're ingesting data, and TimeStream will kind of figure that out and store the data appropriately. Whereas if you were using a SQL store to store your time series data, typically what you see here, and you do see this a lot, I've done this a lot in my past as well, it's pretty convenient to do this, especially if you have other data already in your SQL data store that you would want to join with. Then it makes it a lot easier to have your time series data also in that store. And what you typically have is tables with one row per measurement. So each of these attributes would also be, in a kind of denormalized view in that row. And so you can kind of see that these dimension values would be repeated for each measurement, which that can grow a bit costly because you're storing a lot more data in that case. And then also you have to read through that data when you're doing queries. Typically, you see here that you'll add an index for the time column. And you'll probably also want to add other indices too on some of the dimensions so that you can have query based on those dimensions. This also gets a little bit hard to balance because you don't want to add too many indices and kind of have bloated indexes, and then on ingestion that will cost a lot. But also you do need to leverage these indices at query time, or sometimes the queries can just get way too slow. And then one of the other problems that you can run into using a conventional store here is kind of the nature of time series data is to grow over time. As time moves on, you continuously collect more and more measurements. So what you see here, people tend to partition by time, so partition their tables based on time. And then that helps tables not grow too long. You can kind of prune those tables over time. These solutions are still really hard to get right. You have to do a lot of tuning of the indices and how you're doing partitioning. So it's a bit simpler to use a purpose-built store that handles this type of data for you. You can also see too, using a column-oriented format where you'll store kind of all the data points for measurements in one column, and then you can kind of query just for that column at a time. But you still run into a number of challenges too of how you partition the data in an efficient manner.
Okay, so one of the things I read said that TimeStream partitions data by space as well as time. Was that physical, like geographic space, because you mentioned regions, or is it something more abstract?
It's a bit more abstract. So to go back to why you would want to partition data, you partition data essentially in data stores in order to scale ingestion, storage, and query. And typically what we see for time series data that you would want to partition based on time, because this allows you to kind of have more parallelized reads. And also the queries all tend to be around the time element. So it makes sense to be able to quickly determine what data points are relevant to serve your query and just have the query engine read those partitions. But for most time series that we see, there are exceptions to this, but a lot of times the data that you're ingesting is at or around current time. And so indexing or partitioning just by time isn't really sufficient to distribute the ingestion traffic across your fleet if you're seeing a lot of ingestion throughput to a table. And then also at query time, you do want to be able to also kind of scale out queries so multiple workers can read multiple partitions if you are serving a query that has a kind of longer temporal window. So you want to partition as well by some other attributes and how you use the dimensions and the attributes on those time series to determine how to organize the data. So how TimeStream does this is what we call partitioning by space and time. And the way to best kind of understand this is to picture a 2D grid in which all of the data points for your table will live. And along the x-axis is your time axis. And then the y-axis would be what we call the spatial dimension. And for all of the time series that you have in that table would consist of dots that go in horizontal lines. So the horizontal line would represent one time series, and there would be a data point at the time point in which the measurement is taken. And how we want to organize the different horizontal lines or time series are just by similarity. So storing all of the data points similar in time for one time series together, and then also storing similar series close together, because those are more likely to be queried together. And then kind of when we do our partitioning, we will kind of cut this grid into other 2D boxes and store those as partitions, so that we can really quickly look up in our kind of 2D index to figure out where the data is located. And then when we're doing reads, we're pulling hopefully just the data that we need to serve that query, and don't have to do a lot of pruning after we get the data points from that partition.
Okay, I think we're straddling data modeling and ingestion. So let's dive into ingestion some more. At the beginning, we mentioned consumer devices. I imagine ingestion is different depending on the number of sources being ingested. So maybe it's one data center that's putting out a lot of metrics, or maybe it's 1 million consumer devices. How does ingestion process differ, or what are the challenges of these two extremes?
So yeah, there's definitely two types of cases that you see for time series data, where you can have millions of IoT devices out there all sending metrics to the same table, and then also the case where you have a really high rate per device of time series data being produced. And this I'm familiar with the latter case in my time before Amazon, working in the self-driving car industry, because you really see a lot of these in the robotics industry with really high frequency sensors that are collecting a lot of data, really high volumes of data being produced. At one point, I think we were collecting hundreds of megabytes per second per car. So ingesting all of that, you need to be able to handle large batches of data coming in. The former case is really tricky as well, because you have really high throughput of data, and you need to have large ingestion fleets that can handle traffic from many devices, and also ensure that you're not having a lot of fan out afterwards into your storage layer. So how we kind of handle this is with our ingestion auto scaling. So we use these kind of 2D partitions that we just talked about, and how we determine how we slice them further and do further partitioning based on the ingestion throughput that we're seeing at any given time to a table. So for instance, if we're seeing, so I guess first for terminology, we refer to any of these partitions as tiles. So I may be using that word a bit. But if we see a lot of ingestion pick up to one tile, and we see that the resources that we may be constrained in the resources that are able to accept that ingestion throughput, what we'll do is we'll again split that tile into two tiles that can serve essentially twice as much throughput. And we'll continue doing that over time to kind of distribute our ingestion traffic so that we can still serve these really high throughput use cases.
Okay. You mentioned the frequency of data coming from these self-driving cars. What sort of frequencies are common in time series databases? For example, high-frequency trading operates at the scale of milliseconds. What frequencies do you typically see?
It definitely varies by the use case. We see sometimes even the need for nanosecond precision, and that's what we support in Timestream is up to nanosecond. It really depends on the use case. Sometimes we see use cases where maybe you only have a metric per hour or even per day, and that we certainly support. But some of these really high frequency and where you need that sort of time precision use cases, maybe even like the monitoring use case too, where you have systems that are really low latency themselves and are producing metrics at faster than at the millisecond level. So we do support nanoseconds.
Okay, this might be straddling the topic of ingestion and queries, but once data is ingested, how quickly does it need to be queryable, or how quickly can it be queryable? And just what challenges are there in making the data available as fast as possible?
For many use cases, you want the recently ingested data to be available in under a second. There are a number of different customer use cases out there that are very time sensitive, such as if the monitoring use case. If you're monitoring your e-commerce site on Black Friday or Cyber Monday, I guess it is, you want to know if there are any issues immediately, because you could be losing hundreds of thousands of dollars, millions of dollars per second that your site is down. Also, other real-time analytics use cases, or say if you're doing fraud detection on different purchases, you want the latest data to be serving these predictions. You don't want data from an hour ago. You don't even want data from 5 minutes ago. So getting the data ingested and queryable is really, and doing that quickly is really important. And there are a lot of challenges with doing this, the same kind of with any distributed data system, where you, the top priority of any data system is durability. So you need to ensure once you ingest that data that it is correct and durable. And so you'll want to, have redundancy in your system. So you're storing replicated copies of that data and ensuring it's consistent when customers go to read that data. And how we do this for Timestream is we have all of our ingestion coming into a fault-tolerant memory store. So a single kind of writer node will accept writes, and then we will replicate that out across 3 different availability zones and have quorum-based consensus so that we can handle a node going down or an entire availability zone going down. And then that allows us kind of serving the ingest traffic in memory to be really fast with how we are able to ingest the data and then make it instantaneously queryable.
Support for this episode comes from SingleStore, the single database for all data-intensive applications. Why make the switch? Scaling modern SaaS is already hard. It's even harder when you're using databases that were built back when all your friends had pet rocks and the most stressful part of your day was connecting to the dial-up modem. SingleStore is built for the smart SaaS generation and all the data-intensive applications that come with it. The SingleStore Cloud powers the new wave of SaaS technologies, displacing legacy providers with insights for apps, effortless operation of models at scale, and easy shifts to the cloud. Introduce simplicity and ease to your data structure and watch what happens to your speed, scale, and SQL. Find out why industry leaders trust SingleStore to modernize their data platforms. See for yourself at singlestore.com/try-free.
So scale is obviously an important topic here. Can you describe what difficulties does scale present to the ingestion process? Let's suppose we have many data sources and they are all high volume. So the total amount of data being ingested is huge. How can you cope with that?
Yeah, so we have seen some use cases with Timestream where we see really massive amounts of data coming in at one time. So workloads where we see gigabytes per second per table coming in. And you can't really handle that volume of data without distributing the load in some fashion. And how we do this is we distribute the load by cutting more into our 2-dimensional space of tiles. So in order to really increase, if we're seeing a lot of increased traffic to these tiles, then we will further split them down so that we can have more resources working on ingestion for that table. And then similarly, if we see workload decrease to the table, then we can merge tiles back together so that we don't have resources not working on a lot of incoming data. And by nature, time series data is also somewhat interesting to versus other data that you see like in online cases, because most of the time series data is immutable and also coming in order at or around current time. There are a lot of times when this is not the case, so we do need to support data updates and data deduplication if we are receiving duplicate data points, and then also supporting out of order data or even data that could be really old. But a lot of times time series data does come in this fashion, so that allows us to really scale our system and not have a lot of conflicts when multiple different hosts are kind of getting the exact same data points that they need to ingest. But we do have to deal with this case, and we do have a manner of doing kind of batching and load balancing with our ingestion service.
So I think I hear you saying that it's not just the volume of data, it's the dynamic range that you have to be able to support the amount of data becoming more or less as it proceeds.
Yeah, that's true for systems that are such as TimeStream, where we don't know upfront what workloads to expect from customers, that it can really be dynamic. And we want to ensure that we're being cost effective in the resources that we're using, and also can scale up really, really quickly to support any fluctuations in workloads from customers.
Okay, I want to talk a little bit about lifecycle management. When I was reading about time series database, I found it interesting that many times customers choose to age out their data. Is this strictly because of storage costs, or are there other reasons?
Typically, you see this is due to storage costs and the fact that you may not have a business use case for the older data. So the nature of time series data is to continually grow as time moves forward and you're collecting more and more measurements. And sometimes the older data that you have could be large in volume and expensive to store. And if you don't need to query it, then it can make sense to age out of your system. Also, sometimes you see that the raw data measurements that you're ingesting can sometimes be really high in volume. And these can be, expensive to store all of the raw data, and then also expensive to repeatedly scan all of that data at query time if you're doing some of the same queries over time. So you see use cases where instead of storing all of the raw data for a long period of time, you run queries on kind of roll-ups of that data and store those aggregations somewhere that has a longer retention, and then have a shorter retention on the raw data.
So that being said, are there use cases where 100% of the data is kept indefinitely?
Yes, there are certainly use cases where you would want to keep the data forever. Thinking the medical industry or financial industry, where you may have legal or compliance reasons to keep the data indefinitely. And then also the data could be really useful. I think a lot of times time series data could be used when you're training an ML model. And a lot of times you'll want as much data or as many unique events as possible for training data. And then sometimes too, if you have like rare events in that historical data sample. So maybe if you're training a weather forecasting model and have some like really rare weather events, you'll want to keep that data for longer. I remember one time working in self-driving car industry, and the power went out in San Francisco, and we really wanted to ensure that we retained all of the data we collected during that time, in which all of the traffic lights were down in the entire city. So cases like that, I think those exist.
That makes sense that different industries have different compliance or business use cases. So I read about hot data versus cold data. Does hot data mean it's stored in RAM and cold data mean it's on disk, or is it not always that straightforward?
Typically with time series, when you're talking about hot data, you're talking about the online use case where you're doing real-time analysis on the latest data or monitoring of the latest data. So for that, it's the latest data. So this is the data that's just been written. You need really fast writes. And then also you want these queries to be really fast, returning in milliseconds. So to get this type of performance where you have really fast writes and really fast reads, I think typically you would store the data in memory in that use case. And then this is more expensive to store data here versus storing the data on disk. So then I think that's why you would typically want to push the older, more historical data that is serving a lot of the offline use cases onto disk at that time. So kind of your cold data on disk. And this data can kind of cover larger time periods. The needs for querying aren't as low latency as the online use case, and then kind of storing in a read optimized format since you're typically serving more reads off of this data. And Timestream manages this with two different data stores that have two different retention periods. So Timestream has two tiers for storage. One we call the memory store. And this store, stores the data in memory, the most recent data. And then we have a magnetic store, which stores the data on disk. So when a customer is setting up their table for their time series data, they declare the retention periods for the memory store and the retention periods for the magnetic store. And then the Timestream itself takes care of moving the data around, querying between the two layers. And this is all pretty transparent to the user, other than the memory store will have faster query performance. And that will cost a bit more for storage as well.
So you mentioned the real-time analysis of recent data. What is the relationship between time series databases and visualization tools like Grafana? What do you see customers using with their time series database?
Yeah, I think it's very natural for us when we're thinking about time series data to think in terms of how to visualize that data. Even thinking of our example of financial data, and you're probably thinking of like the stock tracker where you can very easily visualize with a line on a graph of the stock price plotted over time, of it rising or decreasing or crazy spikes and that type of thing. So that's very common for all sorts of time series data. And having tools like Grafana to visualize this are really, really useful, especially when in the case where you're monitoring or building reports for your data. So for the operational metrics, when you're monitoring a system, Grafana is a common tool to use here, and other tools like it where you can easily create a dashboard that allows you to have a lot of aggregate metrics over time. And this, the query language for these is really natural for time series data, where you can, do these aggregate percentiles or averages, do groupings by different dimensions, doing roll-ups by minutes or hours or day. They auto refresh. They're much easier to use versus maybe like handcrafting SQL and sending SQL queries against the data store, or looking at the raw time series data itself. And there are also a number of business intelligence tools as well that you can use for reporting or doing analysis on against time series databases. Timestream has integration with Amazon QuickSight and a number of other tools. And we do support a SQL query interface with a lot of extra time series specific functions, and have support for JDBC driver. So a number of different BI tools you can hook up to query your Timestream data.
So when we're talking about querying recent data or live data, what type of query performance do people expect compared to, say, doing a report on the historical data?
So for querying live data, you would expect query responses in milliseconds. And for these, you're querying typically maybe tens of gigabytes or fewer data points. And so this is the data that you typically have stored in memory that can really quickly serve these data queries. Also, for this use case, you tend to see a lot of concurrent queries as well. So thinking of if you have a Grafana dashboard that's monitoring your system, that each time it refreshes every minute or so, maybe sending tens or hundreds of queries to the data store that you want returned immediately almost. And then when you're doing kind of more ad hoc analytical queries or maybe fetching data for ML training, you can scan a lot more data. So you can scan terabytes or even petabytes of data, and the latency requirements aren't as strict here. Seconds is acceptable. And how we handle those with Timestream 2 is having an adaptive distributed query engine that will auto scale based on the type of query that we see coming in. So it does some estimation on how complex is the query and how much data, how many of these 2D tiles is the query going to need to fetch. And then it can distribute that load out of a fleet of workers. So what we've seen kind of benchmarking this is as the amount of data that we see, as the data volume that we query grows, the query latencies themselves don't grow nearly as fast.
We've been talking about performance this whole time, but let's dig even deeper. I can imagine that ingestion performance and query performance are very different things. Which matters most, or how do you balance providing these two things?
So what we see for a lot of time series use cases are that both really matter. Both ingestion and query performance tend to matter. You can see this with a number of different use cases. So suppose we have some real-time analytics use case, or say we're doing fraud detection on incoming data. And for that, we need both the ability to act upon the latest data, so writes to be really efficient, and then also reads to be really fast so that we can make our predictions very fast. We've seen this too with the video streaming service that uses Timestream for monitoring, where if they are about to release, maybe a new TV show is about to come out, they'll expect a lot more users to be watching that at the time that it's released, and that will produce a lot more data for monitoring. And then also those are kind of the critical times for their service to be up and running. So what you tend to see in many of these use cases is that both really matter for performance. And that's one of the things for Timestream, where we've built the system so that we can scale both of those separately, and also benchmarked really high loads for both write and read together to kind of test out these real world cases.
Yeah, I read you need to be able to scale ingestion, query, and even storage separately. Is this to support different customer types, or is one customer going to need these different things over their lifetime?
It depends. I think having the ability to scale separately allows us to dynamically respond to what workloads we're seeing, both for ingestion, query, and storage. There are use cases where you may see both heavy ingest and query that we just talked about, but there are also use cases where maybe you are just having heavy volumes of queries. So I'm thinking if you have a use case where you're doing a lot of training of ML models or really heavy analysis against the historical data, so you'll want to be able to still independently scale your system to support those workloads.
Okay, we talked about storing data in RAM or disk. How specifically does the developer configure where that split should happen? Is it just a question of time, like all data that's older than 1 day is stored on disk, or is it more complicated?
It's typically a matter of time when we're looking at the table level. That's how Timestream manages it, is that with the developer setting up the table, will set a memory retention period and a magnetic retention period. And when data is older than the memory retention, we'll age that data to the magnetic store. And these values are just time durations. So typically, based on the use case, you'll set maybe a day or 30 days or maybe even a year for your in-memory store. And then that will be kind of a sliding window from now that will age out data older than that period. And this is kind of more, it varies a lot based on the customer use case of how you're using this data and what the query patterns are. And what we see is that if you do have multiple use cases, then a lot of times naturally those time series will fall into maybe two different tables, and you could have different retention settings for those tables.
Okay, we talked about SQL databases early on and how they're likely not going to scale with a large time series application. But what specifically about queries is faster with a time series database compared to SQL?
Yeah, so what's faster than conventional databases is how the data tends to be stored. So what time series databases do is really optimizing how they store data. So such as storing all of the data points for one series together and then storing the similar series together so that when you're serving a query, you're able to just read the data that's relevant for your query, and then really efficiently indexing this data as well, so that you can quickly, we have a 2D indexing that maps into kind of our 2D time and space grid where we store all of the data points. So what we want to do when queries come in is really efficiently be able to look up where the data is and then quickly prune out the tiles that aren't relevant to serve that query, and then have kind of the minimum amount of non-relevant data points in the tiles that we do serve back. And then also another kind of the query engines too, this is probably common with conventional databases as well, but being able to really distribute queries is also really important to keep query performance good as the data set grows, because with the time series use case, we know for a fact that as time goes on, we'll continue growing and growing that data set. So being able to massively scale out data queries over time is also really important.
So moving on from performance, Amazon TimeStream is a serverless database. What advantage does a serverless implementation have for the user?
Yeah, so one big benefit of serverless, and this somewhat goes into performance and auto-scaling, is that the user of a serverless data store doesn't have to think too much about what type of load they need to support in advance. So there's no resources that they need to provision. So they don't have to think in advance, how many nodes does my data store need to be on? What type of instance type do I need to have good performance to serve the ingestion and read traffic for this data store? And they don't need to manage scaling up when they see increased usage of the time series store, nor worry about scaling down when they see less usage and don't want to pay for being over provisioned. So this is really helpful for users of databases, just to not have to manage the instances themselves and scaling those up and down. You only pay for what you use, which is nice. And I think this is really helpful, especially for different data teams at companies, because it's really hard for time series data to do upfront capacity estimation. Thinking of, you have to work with all of the different teams at your company to understand what their time series usage is, and then kind of plan ahead for what their ingestion volume will be, what their storage will be over time, and then also how they expect to query that data. And that's hard to do in an accurate manner. So it's then hard to ensure that you have the capacity that you need and that you're not paying to be over provisioned. I've seen this before working on data teams too, that it's really difficult to get accurate estimates, especially if teams aren't yet using the solution. So being serverless really helps with this, paying for what you use. And then also it helps with just the operational load where you're not managing the resources themselves. So a lot of times managing databases is a non-trivial amount of work where you have to keep it on the latest patches. You have to make sure it's highly available. These are difficult operational tasks.
Yes, I guess, again, we're talking about the dynamic range of how much data the company or the user is processing. And I can see if that varies a lot, that serverless is going to be potentially easier to manage. I read that TimeStream is cell-based. Is that the same as tiles, or is that something else related to architecture?
That's something else that's related more to the architecture and the infrastructure that Timestream runs on. So this is a pattern that is used at AWS. I think Aurora uses this as well. But how we've architected Timestream itself is to run as a full system in multiple isolated, what we call cells. So the system itself is segmented into multiple copies of itself, and customer traffic coming in will just go to one of these copies. So what this allows is each of these cells runs in an isolated fashion. So if there is an incident in one of the cells, then it won't impact any of the other cells. And why we do this is in the case that there is an incident, this really dramatically reduces the blast radius.
We haven't mentioned security at all. How does a serverless design impact security considerations?
Yeah, so a serverless design can help with the customer of a database and not have to worry as much about the different security implications, since they're not managing the resources themselves. They're not managing the instances or the storage nodes. They don't have to ensure that those are secure, running the latest software, managing access to them. The data store manages all security at kind of the top level. So for Timestream, we're secure by default. We encrypt data both in transit and at rest by default. And customers can bring a key to encrypt the data with them, or they can just leave that completely to Timestream to manage. So this really makes security, I think, a lot more simple for customers being serverless.
Great. Okay, let's start wrapping up. What are some trends that you have noticed in time series databases? Where do you see things evolving in the next 3 to 5 years?
Yeah, I think where we'll see a lot of evolution in time series databases is just their growth and adoption. I think right now we're just getting started in terms of usage of time series databases and the functionality that they can serve. And if you think about it, so much data out there across so many industries is time series in nature. And, most data that you're collecting has some sort of time element that you tend to not so much care about the current state of things, but you want historical data as well. And especially as machine learning expands and we make devices and different operators smarter and smarter, kind of giving them insight into this historical data as well is really important. And I think another area that we'll see is as time series databases are more well used, that we'll see more use cases erupting right now as well across different industries. So I think that's really an exciting area to see what all we'll be using time series databases in the future.
Yeah, I can see adoption being something that's going to accelerate. Is there anything we missed that you'd like to mention?
One thing we didn't talk a lot about was just the types of queries that you typically see and the types of analysis that you do on the time series data. And I think that's a really interesting area. So to talk a little bit about what types of queries you would run on time series data, a lot of times what you're doing is doing aggregates over time, or maybe filtering by some of those dimension attributes. So if we go back to our observability use case where you're monitoring a system, you may be looking at what is the 90th percentile of CPU utilization across the hosts in my fleet for this region. And you can do things such as alert if these values go above a certain threshold, or just plot these values out on your dashboard and have a lot of them. But also what we see are some even more complex analyses that you do in real time on top of time series databases. So some of these examples are looking at forecasting. So being able to, if you're a ride sharing service and demand picks up in a certain area, forecast how that will continue growing or not growing, and then maybe changing the price of your service or sending more drivers in that area. And there are certain query types too that are a bit more complex in time series data. such as looking at derivatives on top of time series data, so measuring rate of change, integrals, if you're looking at maybe totals over a period of time, if you're maybe having something like sales per second or per day for your e-commerce site in your time series and want to total per day how many sales you have, you can use that. You can also use correlation functions to compare to time series. That's useful if you're kind of looking at trends between different similar time series. Also, interpolation is another one that's really helpful if your time series is missing data points and you need to kind of fill those in. So there's a lot of really cool queries that you see done on this time series data that I think if you're interested in this is worth looking into. And I think these are really powerful queries that will also we'll see evolve over the next 3 to 5 years as people are leveraging this time series data more.
I can see that's interesting. So there's a dynamic range in the data being ingested, but it sounds like you're saying there's also this dynamic range in queries where you might be looking at second to second or minute to minute, but you might also be looking at trends that last months or even years.
Yep, that's correct. Yeah.
Great. Where can listeners find out more about you or Amazon TimeStream?
Listeners can find out more about me. Probably the best way would be to look me up on LinkedIn. My LinkedIn URL is just Audlaw, AUDLAW, and then I'm Audrey Lawrence on LinkedIn. Also, a little bit of plug, if any of these problems sound interesting to you, we are hiring, I'm hiring software development engineers and software development managers for my team. And there are many really exciting problems we're working on in this space. So please ping me on LinkedIn if you're curious about this. And then for TimeStream itself, we have public docs that detail different use cases and different integrations that we have. Also, if it's really easy to go and get started, you can, with a couple clicks in the AWS console, create a database, create a table, and even seed it with some data from some sample data that we have for a couple of different use cases, and then start playing around with queries if you want. And then there's, I think on GitHub, code samples in different languages too, if you want to directly use our APIs in any of the AWS SDKs.
Great. I'll put your LinkedIn in the show notes and some links to some of these TimeStream resources. It was great to have you on the show, Audrey. This is Philip Winston for Software Engineering Radio. Thank you for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.